Find the area of the shaded region. We have two congruent circles of radius tangent to each other and connected by two tangent segments. There's no straightforward formula here, so we'll rely on a geometric property instead. The radius to a point of tangency always forms a right angle with the tangent line, and by drawing a duemeter parallel to the tangent segment, we can construct this square with side length equal to the radius. We also recall the area formula for a circle, pi times the radius squared. We begin by connecting the centers of the two circles, forming a segment composed of two radii of length 10. Next, we connect the centers to the points of tangency. Next, draw a line parallel to the diameters through the point, where the two circles are tangent. Notice that ABCD forms a square, because the tangent segments at the top and bottom are both equal in length to the diameter of these circles. Now observe that the shaded region is exactly equal to the area of the square minus the areas of the two semicircles. But two semicircles together form one complete circle, which makes the calculation much simpler. So the shaded area is simply the area of the square minus the area of a circle. The side length of the square is 20, so its area is 20 squared, which equals 400. Each circle has a radius 10, so the area of the circle is 100 pi. Therefore, the shaded area is 400 minus 100 pi, which is approximately 85.8, and that is the desired area. And what makes this problem especially interesting is that the solution does not rely on advanced formulas or complicated techniques. In fact, the entire argument comes from just a few simple geometric ideas used in the right way. The key observation was recognizing the relationship between a radius and a tangent line. Once we used that 90-degree property, the hidden square naturally appeared inside the figure, and from there, the problem became much more elegant. Instead of dealing with irregular shaded regions directly, we transformed the figure into something easier to understand, a square minus a circle. This is one of the beautiful aspects of geometry. Very often, difficult-looking problems become simple once the correct construction is introduced. The goal is not just calculation, it is learning how to look at a figure and discover the structure hidden inside it. In this example, we only used basic logic, the area formula for a circle, and a classical property of tangency. Yet those small ideas were enough to completely solve the problem. And that is why geometry remains so fascinating. Simple observations can lead to surprisingly elegant results. If you enjoyed this problem, there are many more beautiful geometric constructions and proofs to explore. Thanks for watching.